Hello there, and welcome to Just About Earth, the place where ancient oceans lap at your ears and curiosity takes the slow scenic route towards sleep. Tonight we're setting off on a journey, not through fire or flood, but through something quieter, stranger. A chapter of Earth's history that's been quietly nicknamed the Boring Billion. Imagine calling 1 billion years boring. That's a stretch of time, so long your favorite mountain range might have risen, eroded, and risen again, while microbes kept humming along in the background. But what if it wasn't boring at all? What if beneath that stillness, life was quietly rehearsing the miracles to come, inch by inch, breath by molecular breath, crafting the ingredients that would one day become forests, animals, and us? Before we dive in, though, a little question for you. Where are you listening from tonight? And what time is it where you are? Fitting, isn't it? A story about deep time. And here we are scattered across little personal clocks, each of us arriving at this very moment together. If this gentle exploration helps your mind settle, or even just gives your thoughts a soft place to rest, I'd be ever so grateful if you'd like the video or maybe subscribe. It helps this quiet little channel find others who might also enjoy drifting off to the sound of ancient plate tectonics and sleepy science. So settle in. Let the day fall away like dust from an old book, and let's begin. Because somewhere, buried deep in Earth's slowest, quietest years, lies the secret to everything we've become. Sometimes scientific revolutions don't start with explosions. They start with something quiet, a needle twitching, a compass hesitating just slightly on a rock face older than trees. It's late afternoon in a field lab in northern Canada. The wind murmurs across the boreal forest, and inside a small wooden shed, a geologist sets down her coffee and frowns at the compass in her hand. It wobbles just for a second, as if remembering a magnetic field long forgotten by Earth's surface. She's standing over a long cylinder of stone, a core sample pulled from nearly 2 kilometers below the crust, each layer a whisper from the past. From the look of it, this one's very old. Protozoic, perhaps, somewhere around 1.44 billion years, a time most textbooks rush past with barely a paragraph. And yet, the compass is whispering that something here is strange. Not long after, she ships a slice of that same rock to a lab in Europe, where it will be polished flat, scanned with lasers, bathed in acid, and examined down to the atomic level. The results, when they come, seem subtle. A hint of remnant magnetism pointing in an unexpected direction. Oxidation levels that don't quite match the assumed anoxia. The trace of ancient microbial mats where there should have been chemical dormancy. Word spreads as gently as this kind of science ever spreads. And in research labs across the world, people start pulling old samples from shelves. Core archives from Australia, from China, from Africa. The same pattern emerges like a hum that was always there, but finally reaches the edge of hearing. It turns out the Boring Billion might have been doing something after all. We call it that, the Boring Billion, because for a long time, we simply didn't know what to say about it. Between about 1.8 and 8 billion years ago, the geological record seemed quiet. No dramatic rise in oxygen, no great extinction, no multicellular explosion. 1 billion years with no major landmarks, a geological desert, a lullaby between Earth's louder verses. If Earth's story were a novel, this would be the chapter most readers might skim. But science, like sleep, rewards patience. It waits. And slowly the boring part of the story began to blink back at us. To understand how we got here, to this realization, this shift in tone, we have to rewind a bit to an earlier clue. It came not from a compass, but from iron in ancient banded iron formations, those red and gray striped rocks that once lay at the bottom of oceans long gone. Scientists noticed something odd. After the Great Oxidation Event around 2.4 billion years ago, those formations seemed to vanish. The oceans, it was thought, had changed. Oxygen had flooded in, Iron had rusted and settled out. Banded formations had given way to carbonate shelves, and the world had supposedly moved on. But then quietly in scattered outcrops from the Congo Basin to the Flinders Ranges of Australia, geologists found them again, not in the aftermath of catastrophe, but in the middle of that uneventful billion. The boring billion wasn't as iron-y as it was supposed to be. These ancient seas were still anoxic, still chemically alive in ways we hadn't understood. Iron was still dissolving, still reprecipitating, still holding conversations with the early biosphere. Meanwhile, over in Princeton, a paleobiologist named Tanya Bosak was working with bacterial mats, not fossils, but modern analogues, trying to understand how ancient life might have shaped sedimentary structures without leaving bones or shells. Her lab recreated Proterozoic conditions in aquaria, dimly lit tanks filled with iron-rich water and clusters of cyanobacteria. What they saw was stunning. Even under low oxygen, microbial mats could build laminated structures nearly identical to strumatillates. Fossils we once thought indicated oxygen abundance. Maybe, just maybe, the biosphere was still active during the boring billion. Maybe we just weren't listening closely enough. It's not just chemistry and bacteria that crack the silence. Physics joins the conversation. In one study, a team from the University of Rochester reanalyzed ancient zircon crystals, some of the oldest minerals on Earth, and found embedded traces of uranium decay chains that hinted at deep crust recycling even during tectonic lulls. These crystals formed in granitic rocks laid down during a time previously thought tectonically sleepy. They suggested that continental plates weren't just resting. They were inching across the globe with the slow determination of glaciers colliding gently, raising low mountains that may have fed ancient rivers with the trace elements life needs to dream bigger. And that magnetic clue, the wobbling compass, that too turned out to matter. In a groundbreaking 2018 paper, a team from Harvard proposed that Earth's magnetic field during the boring billion was weaker and more unstable than today's is. That might sound abstract, but it could explain everything from atmospheric escape to the distribution of early nutrients. A feeble magnetic shield would have let more solar radiation strip away hydrogen, drying out the upper atmosphere and slowing oxygen buildup. A hidden hand holding the biosphere in place, keeping evolution simmering instead of boiling. Suddenly, the billion began to look more like a pot set to low heat. Not boring, just slow-cooked. Even the continents, those lazy tectonic rafts we assumed had drifted into torpor, turned out to be stirring ever so slightly. A new round of paleomagnetic reconstructions showed that Rodinia, the supercontinent forming during this period, wasn't as static as once believed. Its edges were dancing, just very, very slowly. Enough to create localized rifts and basins, enough to trap nutrients in shallow seas, enough to let microecosystems flourish out of sight of dramatic extinction or innovation, but rich with the gentle trial and error of early eukaryotic life. And now the threads begin to knot together. You have iron still cycling in deep waters. You have oxygen pulses flickering in and out of shorelines. You have eukaryotes, not yet multicellular, but growing in complexity, learning to handle internal membranes, to share organelles, to flirt with genetic recombination. And you have a world in which the rules of survival are consistent enough, stable enough for slow innovation to thrive. In short, the boring billion might have been Earth's training montage. Not flashy, not loud, but critical. Which brings us back to the people who helped us see it that way. Not all science is done in dramatic bursts. Much of it happens in hallways, in emails sent with 6 attachments and cautious optimism, in conference talks where someone shows a sulfur isotope ratio that doesn't quite fit. And another researcher's eyes light up because they've seen that pattern too half a world away. Take James Farquhar, whose work on mass-independent sulfur isotope fractionation revealed atmospheric shifts during the Proterozoic that nobody had expected. Or Malcolm Walter, whose fieldwork in ancient Australian stromatolic beds helped redefine how we recognize microbial life in the fossil record. Or Noah Planovsky, who pieced together chromium isotope anomalies in black shells to reconstruct ancient redox conditions and oxygen oases. Each of these contributions is a lantern. When lit together, they show a landscape less like a desert and more like a quiet forest, full of slow growth and hidden symmetries. And like many scientific landscapes, it wasn't just built from rock. It was built from doubt. The boring billion became a puzzle, not because it shouted, but because it didn't. Because it dared us to listen to whispers in shale, to notice a pattern in seemingly unchanging strata, to ask whether silence might also be telling a story. Maybe that's the trick of deep time. It doesn't always leave you with a grand reveal. Sometimes it just hands you an ancient rock and asks you to sit with it a while. And when you do, when you brush away the dust and take a closer look, you might find that what looked like stillness was simply a slower form of movement, a kind of planetary patience. The Earth was not asleep. It was simmering, and something was preparing to wake. Close your eyes just for a moment and try to imagine a world without trees, without animals, no birds in the air, no insects in the soil, no fish beneath the waves, no grasslands or predators, no flowers or fungi or forests. Only the long hush of time, broken by the ripple of warm water on ancient shores and the slow breath of a sky just beginning to change. This was Earth 1.5 billion years ago. To step into that world is to walk into something both alien and familiar. A planet wearing the same blue face, but holding a different rhythm in its heart. The sun hung dimmer in the sky, perhaps 10% weaker than it is today. But the greenhouse gases swirling through the atmosphere kept the oceans warm enough to cradle life. The moon orbited closer, tugging at the tides with greater pull, and the days themselves were shorter. Each sunrise and sunset racing across the horizon in just 18 hours. The Earth spun faster then, like a younger dancer, still full of momentum. If you stood on the edge of one of those early continents, perhaps part of the supercontinent known as Nuna or Columbia, depending on which map of deep time you prefer, you'd see land that was low and quiet. No towering mountain chains, no alpine drama, just gentle slopes, soft hills worn down by a billion years of earlier weather, surrounded by tidal flats where microbial mats clung to every sunlit surface like thin living carpets. And those mats, those strange slimy colonies of cyanobacteria, they were the architects of the future. They pumped out tiny amounts of oxygen during the day, photosynthesizing in the shallow light. Then, as night fell, they went quiet again, letting the iron-rich seas reclaim the upper hand. Over time, their breath rusted the oceans, forming red bands of iron that would settle into stone. Layers we still dig up today. Clues to a planet trying to teach itself how to breathe. But in this world, that breath was never easy. The atmosphere above would feel thin and accurate to us, not because of some dramatic poison, but because of what it lacked. Oxygen, that quiet enabler of complex metabolism, was present in barely trace amounts, perhaps 1–2% of modern levels. It hovered mostly near the coasts, just enough for rust and respiration to tease each other in a slow evolutionary tug-of-war. Further out in the deeper oceans, the water was dark and sulfidic. Scientists call this a eosinic ocean, where oxygen vanishes and hydrogen sulfide takes over, rising from the sediments like a ghost of decaying matter. The seas themselves weren't quite like ours. Rich in dissolved metals, especially iron and manganese, they shimmered in places with a subtle, almost oily iridescence. If you scooped up a handful of water in a clear bowl, it might appear tinted. Not quite red, not quite green, something between, with flecks of microbial life drifting in and out of view. There were no fish, no shells. But there was life, and it was already astonishing. Most of it was microbial, single-celled, small, and stubborn. Bacteria ruled the depths, thriving in chemical gradients modern life can barely tolerate. Some performed chemosynthesis near hydrothermal vents, transforming raw minerals into energy. Others floated through the photic zone, sipping sunlight, dividing endlessly, forming microbial blooms vast enough to color entire coastlines. And then there were the newcomers. Around this time, within the so-called dullness of the boring billion, a quiet revolution was underway. Somewhere in the soup of early life, a cell had swallowed another, not to digest, but to live alongside. One became two, symbiosis. And inside that cell, a former free-living bacterium began to specialize in energy production. This was the birth of mitochondria, the tiny organelles that power every complex cell today. And with it came the eukaryotes, cells with nuclei, with internal architecture, with the potential to one day become everything from jellyfish to giraffes. They were still small then. Most could fit by the thousands on the head of a pin. But under a microscope, if you'd had one, you might have glimpsed the beginning of structure. Internal membranes folding in upon themselves. Threads of DNA coiled inside protective envelopes, vacuoles, cytokeratins, little compartments of possibility. These cells didn't live alone. They formed colonies, biofilms, communities floating through the shallows or clinging to submerged rocks. Some even began to exhibit primitive cooperation, passing signals, sharing nutrients, fragmenting together. It was not yet multicellularity, but it was a step toward it. A choreography of bodies had begun, one slow pirouette at a time. Above them, the skies shifted. Not fast, not dramatically, but inevitably. Methane, once abundant and warming, began to decline. As oxygen-producing microbes carved tiny holes in its dominance, the greenhouse blanket began to thin. Clouds changed, rain patterns shifted, and in places for the first time, land began to dry and crack in earnest. Soils were still primitive, just dust and minerals. No roots, no worms. But erosion moved nutrients downhill, feeding the coastal zones where microbial life bloomed most vividly. You might wonder about color in such a world. We tend to think of the past in sepia, in grays and browns and dust. But Earth during the boring billion was vivid in its own way. The ocean shallows, dense with microbial pigments, would glow with purples and greens from bacteria chlorophylls, substances that capture infrared light. Under a low sun, those colors could bloom across miles. The sky itself, thinner in ozone, may have appeared deeper blue, or even tinged slightly violet at dusk, with ultraviolet light scattering more freely. Volcanoes puffed sulfur-rich clouds into the air, sometimes dimming the sun with yellow haze. At night, the stars shone with an intensity our modern atmosphere muffles. The Milky Way, a radiant, constant presence overhead, unchallenged by light pollution or satellites. There were no forests to sway in the wind, but the wind itself sculpted dunes across vast arid interiors, carrying whispers from basin to basin. Occasionally, rivers flooded from inland uplifts, carving through barren landscapes and leaving behind rich fans of sediment, playgrounds for microbial colonization. And beneath it all, the crust kept moving. Slowly, yes, but persistently. Plates shifted by centimeters each year, cracking and grinding in long drawn-out rhythms. The heat of the mantle pushed upward in places, forming gentle domes and rifts. These slow tectonic murmurs created basins that trapped nutrients, created upwelling currents, and maintained just enough instability to keep evolution interested. Every so often, a new niche would form. A quiet tidal lagoon, a thermal spring, an isolated salt lake. And in those little pockets, life ran experiments. New metabolic pathways, new ways to reproduce. Occasionally, failures, more often persistence. Even viruses played a role, flitting between cells, shuffling genes, adding their own strange footprints to the tree of life. In this way, even the most invisible actors of the biosphere, the things that don't fossilize, that leave no shells or tracks, still move the story forward. What about predators? At this time, predation was still in its infancy. Most life forms absorbed nutrients from their surroundings or photosynthesized, but some eukaryotes, likely ancestors of amoeba, began to engulf their neighbors. Phagocytosis, swallowing whole cells, was becoming more common. This simple act, brutal and efficient, would later drive evolutionary arms races. But for now, it was just another quiet trial in a slow world. The fossil record here is sparse, not because life was rare, but because the conditions for fossilization were finicky. Without hard parts, most organisms vanished into the mud. But occasionally they left impressions. Microscopic fossils called aciders, mysterious ornamented spheres, dot sediment cores from this time. Some of spines, some of symmetrical ridges. Some seem to suggest coordinated multicellularity. They are snapshots of evolution's sketchbook pages torn and scattered through shale. These acryarchs are beautiful in their simplicity and enigmatic. We still debate what many of them were. Algae, cysts, dormant stages of some extinct lineage. Whatever their identity, they speak to experimentation, to a biosphere trying out new forms, new solutions, new symmetries. And above all, they speak to survival. Because while this world may have lacked drama by our standards, no mass extinctions, no erupting supervolcanoes, no dinosaurs, it was still a world of flux. Continents moved, oceans rose and fell, climate wobbled, and yet life endured. It didn't leap forward so much as it folded in on itself, refining, recombining, preparing. Evolution, after all, is not just about speed. It's about persistence, about waiting out the noise, about building slowly so that when the stage finally changes, you're ready to step into the light. And the light would change. It always does. In the final 100 million years of the boring billion, tectonic activity picked up. Rhoynia began to rift. Oxygen started to climb slowly, then more sharply. The quiet era gave way to something louder. Glaciations, algal blooms, the Cambrian pulse stirring just beyond the horizon. But here, in the long stretch before all that, Earth learned to hold a stable rhythm, to host a biosphere without burning it down, to let complexity simmer without boiling over. And in doing so, it gave the future something to stand on. So no, it wasn't boring. It was patient, and it was building. To understand what ended the boring billion, you have to think like a planet, not a human, not even an animal, a planet. A body of rock and molten iron and shifting crusts, swirling air, trembling oceans, pulsing magnetic fields. Earth isn't simply a home. It's an engine, a restless living system. And like any system, it doesn't stay quiet forever. The boring billion wasn't broken by a single catastrophe. There was no asteroid, no sudden volcanic winter. What came instead was pressure, not in a single blow, but in a rising rhythm. Earth, long held in a delicate, low oxygen balance, began to tip. And that slow tip over tens of millions of years reshaped everything. The first push came from within. Deep below the surface, the mantle was stirring. For hundreds of millions of years, tectonic movement had been sluggish. Slow continental drift. Long-lived supercontinents like Nuna and Rhoynia sliding lazily across the equator. But as Rodinia began to assemble fully around 1.1 billion years ago, pressure built beneath its seams. Hot spots swelled. The lithosphere bulged. Eventually, cracks formed. Long rift zones that split the land apart like bread rising in an oven. These weren't sudden or violent at first, just fractures, faults, lava trickling into the seams. But over time, those rifts widened, separating once joined cratons, flooding new basins, and exposing fresh rock to the weathering forces of wind, rain, and biology. That's where the second push began. When rock is exposed, especially fresh volcanic rock, it begins to break down. And this breakdown, called silicate weathering, isn't just erosion. It's a chemical process that draws carbon dioxide out of the atmosphere and locks it away in the form of carbonate minerals. CO2 dissolves in rainwater, forming a weak acid. That acidic water flows over the land, reacting with calcium and magnesium in the rocks, and eventually washes into the ocean, where it settles into seafloor sediments. This process sounds quiet, and it is, but it's also powerful. Over time, silicate weathering can pull enough CO2 from the sky to cool a planet, and that's exactly what began to happen. As Rodinia fractured and rifting accelerated, more land was exposed to weathering. Tropical rainfall, enhanced by the equatorial positioning of these supercontinent fragments, further sped up the process. Slowly CO2 levels dropped. Global temperatures long held in a balmy middle range began to decline, and the oceans responded. With cooler air came altered wind patterns. Ocean currents shifted. Upwelling increased in certain regions, drawing nutrient-rich waters to the surface. These nutrients, phosphorus especially, fertilized the photic zone, sparking blooms of photosynthetic plankton. These weren't just your average cyanobacteria. By now, complex algae had begun to establish themselves. Eukaryotic plankton, chloroplast-equipped, more efficient at capturing sunlight and converting it into energy. More oxygen per unit of life, and that oxygen started to build. At first, it was patchy. We find evidence in scattered red beds, rocks stained with iron oxides that require free oxygen to form. Some sediments begin to show signs of oxidative weathering, even in land. Chromium isotope ratios shift, a subtle fingerprint that indicates oxygen interacting with soil and sediment. In marine records, we find the disappearance of certain iron formations and the rise of more carbonate deposits. Together, these clues tell a story. Oxygen was rising again. Not in a dramatic runaway spike like the first great oxidation event, but in pulses, surges, and plateaus like the planet was practicing. In some places, especially near shorelines, oxygen may have reached 10 to 15% of today's levels. Still not breathable for us, but more than enough to challenge the chemistry of life. This increase in oxygen would become a driver and a destroyer. Many of the microbes that dominated the Proterozoic oceans had evolved in low oxygen, sometimes even toxic conditions. Some were anaerobes poisoned by oxygen. Others relied on sulfur cycles, metabolizing hydrogen sulfide, living in the delicate gradients between anoxic and oxic layers. As oxygen pushed into these habitats, it disrupted everything. It poisoned old ecosystems, starved out established microbes, and forced a retreat into the deeper, darker, and more stagnant parts of the ocean. But for other organisms, especially the rising eukaryotes, oxygen was a gift. With it, they could run cellular respiration, a far more efficient way to extract energy from food. Fermentation might yield 2 ATP per glucose molecule. Respiration could give you 36. That's a huge upgrade. More energy meant more possibilities. Bigger cells, more complexity, specialization, signaling, even cooperation. What had once been a sleepy ocean of bacterial mats and passive drifters was slowly, almost imperceptibly, shifting into something more dynamic. Life had more fuel now, and it would use it. But Earth is never content with just one variable changing. As oxygen rose and the biosphere adapted, another force joined the stage, sulfur. For millions of years, the deep ocean had been rich in sulfur compounds. Volcanism and microbial activity pumped hydrogen sulfide into the water column. But with oxygen entering the system, that sulfur began to oxidize, turning into sulfate. And sulfate, in turn, became a critical nutrient, one that certain bacteria could use in new and more elaborate metabolic pathways. This set off a cascade of feedbacks. Sulfur-cycling bacteria flourished in newly oxygenated sediments. Their activity further altered redox gradients, changing the chemistry of both deep and shallow waters. At the same time, increased productivity from algal blooms led to more organic matter sinking into the depths where it decayed, using up oxygen and creating local anoxia all over again. In other words, Earth entered a loop. Oxygen surged, life bloomed, organic matter sank, oxygen dropped, nutrients recycled, oxygen surged again. It was not a stable system, but a series of breath-like pulses. Planetary inhalations and exhalations visible today in the chemistry of ancient black shells, banded rocks, and isotope excursions that mark these strange oscillations. In these shifts, entire microbial ecosystems likely rose and fell. We can't see them directly. No bones, no teeth, but we can sense their passing in the fingerprints they left behind. Changes in nitrogen cycling, in phosphorus retention, in the presence or absence of specific iron minerals that only form under certain conditions. These are the fossils of chemistry. And in reading them, scientists begin to see the outline of an ancient drama, a biosphere learning to respond to its own influence. Life had become a geologic force, and Earth was beginning to notice. But there was one more twist in the tale. As Rodinia continued to rift, it reshaped ocean basins and changed how deep water circulated. In some regions, nutrient upwelling intensified. In others, it collapsed. These changes affected productivity, carbon burial, and ultimately climate. Around 800 million years ago, the planet seems to have crossed a threshold. Weathering had drawn down so much CO2 that Earth could no longer hold its warmth. The glaciations that followed would blanket the planet in ice from pole to pole. Snowball Earth. But before that frozen curtain fell, something subtle had happened. In the run-up to that global chill, Earth had begun laying the groundwork for complexity. Oxygen had climbed high enough to support small multicellular life. Algae had diversified. Eukaryotes were experimenting with size, with shape, with adhesion. Some formed colonies. Hollow spheres of cells with rudimentary coordination. Others, like Graponia, left behind spiral-shaped fossils, up to a centimeter in length. Giants by protozoic standards. And all of this was made possible by the changes we've just explored. The rifting of continents, the weathering of rock, the drawdown of CO2, the rise of oxygen, and the feedback loops between life and environment. Earth was no longer a passive world upon which biology survived. It was a biosphere reacting to itself, shaping its own trajectory. And that is where we pause on the edge of transformation, with the planet trembling quietly before the age of snow and the age of animals. Imagine a world holding its breath. For 1 billion years, life had crept forward in whispers. And now, as the curtain drew near its end, the whispers became a tremble. Change was no longer potential. It was pressure. Something had shifted, not in a single instant, but in a chain reaction, echoing through rock, air, and sea. The trigger was not a singular cataclysm, but a tipping of balance. More oxygen, more nutrients, more metabolic energy, and more vulnerability. With photosynthetic life now blooming in shallow seas and organic material sinking more frequently into the deep, something unexpected began to happen. The deep ocean, long a reservoir of ancient chemistry, began to behave differently. In some places, anoxia deepened. In others, it reached upward, threatening the shallows. The oxygen that gave new life also starved the system. A paradox born of abundance. As algae exploded in number, so too did the rate of decay. Oxygen-hungry bacteria stripping the water column of breath. Life, in its own overachievement, began to smother itself. The oceans, vast and sensitive, responded like a mood. Sulfide levels rose once more. Euonia crept inland from the depths. In places toxic waters may have reached the surface, releasing clouds of hydrogen sulfide into the atmosphere. Invisible, poisonous, fatal to any oxygen-dependent organism daring to evolve too soon. We know this not from fossils, but from chemistry. Layers of black shale rich in organic carbon. Strange sulfur isotope signatures. Evidence of a biosphere wheezing in and out of habitability. These weren't extinction-level events, not yet. But they were warnings. The system had grown unstable, and Earth, as always, was listening. Tectonic shifts continued to fracture Rodinia, peeling it apart like soft fruit. As rift valleys opened, entire regions flooded with new seas. These were epicontinental seas, shallow, warm, nutrient-rich, and ideal for life. Here, evolution accelerated. Populations isolated in lagoons and bays found new niches. Genetic drift took hold. Natural selection sharpened. Even without predators or competition on a grand scale, life was being sculpted by variability, by chemistry, by time itself. In these fertile shallows, some of the first steps toward true multicellularity likely took root. Not just colonies of identical cells, but differentiated ones, cells that specialized, divided labor, coordinated function. A hint of what would become tissues, organs, bodies. It's difficult to say exactly when this leap occurred. The fossil record is fragmentary, but within the deep mudstones and ancient phosphorites of the late Proteroic, we find signs. Fossils like Bangomorpha, a red alga with a clear structure of filaments and holdfasts, dating to around 1.5 billion years ago. This wasn't just another drifting cell. It anchored. It grew. It reproduced sexually. Sexual reproduction was in its own quiet way a revolution. Suddenly, variation was not just the product of mutation, but of recombination, the mixing of genetic material between individuals. This allowed populations to adapt more rapidly, to experiment with complexity, to build new features, and discard them if they failed. It's the mechanism that gave rise eventually to the entire tree of complex life. And it may have emerged in the sleepy shallows of the so-called boring world. From here, the feedback loops only grew more tangled. More multicellular algae meant more photosynthesis. More photosynthesis meant more oxygen. More oxygen meant higher productivity, but also a faster drawdown of CO2 through carbonate precipitation. And that meant climate trouble. CO2 is a greenhouse gas, one of Earth's primary thermostats. Remove too much, too quickly, and temperatures plummet. Add in the reflective power of shallow glaciated surfaces. White ice bouncing sunlight back into space, and a cold feedback loop can accelerate beyond recovery. This is what seems to have happened. By the end of the boring billion, the planet began to freeze. This wasn't the calm frost of winter. It was something deeper, something planetary. The oceans themselves began to lock under ice. From pole to equator, glaciers advanced, rivers slowed, seas cooled. The first of several snowball Earth episodes, global or near-global glaciations, may have wrapped the world in silence once more. But this silence was different from the boring billion slow breath. This was not a lull. It was a reckoning. The trigger had been building for millions of years. Tectonic rifting, atmospheric shifts, biospheric overreach. Now, Earth slammed the brakes. And yet, even this crisis would prove in time to be an opportunity. Because beneath the ice, in volcanic pockets and hydrothermal vents, life clung on. Microbial mats huddled near heat. Algae persisted in brine channels. Eukaryotes endured. And when the glaciers finally melted, their retreat released a flood of nutrients. The ultimate ecological reset button. The world that emerged from this freeze would not be the same one that had gone in. It would be oxygenic. It would be chemically dynamic, and it would be ready for animals. But that story belongs to the next chapter. Here at the end of the boring billion, we see not a world defined by stillness, but one defined by subtlety. A billion-year ballet of carbon, sulfur, iron, and life. A time when nothing seemed to change, and yet everything was changing. It's easy to miss these shifts if you only look for meteors or mass extinctions. But Earth doesn't always shout. Sometimes it hums. Sometimes it changes not by breaking, but by leaning just enough over just enough time to reshape the future. The boring billion wasn't boring. It was the tension before a leap. The breath before the plunge, the planet preparing itself slowly, methodically, patiently for everything that would follow. And that preparation, unseen by most, was the mechanism of change. It's tempting to think of change as immediate as flash and rupture, a crash, a flame, a sudden roar across the sky. But Earth, like a cello, often moves in resonance. Deep, long vibrations that begin almost inaudibly and build until you feel them more than hear them. So it was with the end of the boring billion. Its final movements weren't a clean break, but a gathering of threads. Tectonic, biological, atmospheric, all tightening around a single truth. Balance had tipped. The first real crack came not from above, but from within. As Rodinia, that once mighty supercontinent, continued to rift apart, it carved new coastlines into the land and flooded low-lying interiors with shallow seas. These weren't just geographic shifts. They were ecological openings, entire new theaters for evolutionary rehearsal. Epic continental seas spread across continents like glittering quilts, catching sunlight, collecting nutrients, and warming gently under a still faint sun. These shallow marine zones became cradles, not of diversity yet, but of opportunity. More water meant more evaporation, more rainfall, more weathering of rock. And as silicate minerals dissolved in rainwater, they continued to draw carbon dioxide from the air, cooling the planet. The carbon, now bound as carbonate, settled into marine sediments. Earth's great thermostat was being adjusted degree by careful degree, not by a technician, but by rivers. And meanwhile, life, never one to remain passive for long, Vidamos responded. The increase in nutrients, especially phosphorus and iron, drove photosynthetic life into overdrive. Algal blooms rippled across sunlit shelves. Ancient eukaryotic plankton, still single-celled but metabolically sophisticated, began to thrive like never before. This was their window. The gentle glaciations that had once threatened now gave way to tepid waters and rich feasts. Oxygen, their byproduct, crept upward. It wasn't the first time oxygen had risen, of course. The great oxidation event had come much earlier, around 2.4 billion years ago, a bold experiment in planetary metabolism that had briefly tipped the balance, only to settle back into low levels for over 1 billion years. But this time felt different. With rifting, nutrient flow increased. With nutrients, photosynthesis intensified. And with more oxygen, new biochemistry became possible. Not just for plankton, but for everything that came after. Complex cells began trading genes, developing organelles, and forming partnerships with one another. In the fossil record, acryarchs, tiny ornamented microocels, suddenly bloom in variety and form, spirals, spikes, spheres, and lobes. Their diversity is still debated, but their implication is not. The tempo of evolution had begun to rise. And yet, as is often the case, progress came with consequence. The very productivity that enriched the oceans also began to choke them. Algal blooms created oxygen during the day, but as the algae died and sank, they decayed, using up oxygen in the deeper water column. This led to expanding oxygen minimum zones, regions of the sea where oxygen vanished entirely, replaced by hydrogen sulfide. These zones were toxic to most eukaryotic life and could lead to mass die-offs of entire microbial ecosystems. Earth had entered a dangerous feedback loop. More life meant more death, and more death meant less breathable water. Evidence of these zones appears in layers of black shale, rich in organic carbon, low in iron, speckled with the chemical signatures of anoxia and eusenia. At the same time, isotopic anomalies in sulfur, nitrogen, and molybdenum paint a picture of a biosphere oscillating between flourishing and faltering. An ancient Earth inhaling evolution and exhaling crisis. And it wasn't just the oceans. The atmosphere, too, began to change with CO2 levels continuing to fall and reflective surfaces increasing, whether from ice, cloud cover, or desertified interiors. The planet's energy budget began to run low. Global temperatures dropped. The tropics shrank. Glaciers reappeared in the geological record, not just at high latitudes, but potentially near the equator. Dropstones, pebbles carried by icebergs and released into marine sediment far from shore, show up like punctuation marks in otherwise uniform strata. They speak of floating ice, of a world dipping once more into deep chill. And yet, incredibly, life persisted in subglacial oceans, in brine pockets, in volcanic oases where warmth and chemistry still brewed together. Underneath the planet's newest isolaced silence, the biosphere continued, slower perhaps, but not undone. Some scientists suggest these glacial intervals may have even helped by resetting ecological pressures. Extinction is a brutal editor, but one that clears space for innovation. Meanwhile, the continents, never still, kept drifting. By 750 million years ago, Roenia had fully fragmented. Its pieces began to wander. Some moved toward the poles, others remained equatorial, and their shifting set the stage for new ocean basins and new circulation patterns. The interior of Earth flexed and turned, each plate averse in the ongoing story. And deep beneath the crust, another chain reaction was building. Mantle convection, the slow churning of Earth's interior heat, began to swell in intensity. Hot plumes rose. Volcanic arcs flared. These processes would eventually contribute to large igneous provinces, massive outpourings of basalt that would later reshape climate and trigger even deeper change. But in this moment, the prelude to those eruptions stirred the mantle and fractured the crust. It let more CO2 seep from the deep just as biology had drawn it down. The tug-off war between biology and geology had begun in earnest. More volcanism meant more carbon. More carbon meant more warming. But biology, now oxygenating and growing, kept pulling CO2 back into the crust through weathering and carbonate burial. The carbon cycle wasn't simply geological anymore. Life had inserted itself into the loop, not as a passive reactor, but as a regulator. This is what scientists mean when they say Earth became a co-evolutionary system. Life didn't just adapt to the planet. It began to sculpt it. Feedback loops wove across systems. The carbon cycle, the sulfur cycle, the phosphorus cycle, all increasingly touched by cells, genes, and respiration. This was a critical shift. Earth had become responsive. And in that responsiveness, the possibility of true ecological networks, food chains, webs, resilience began to form. It's difficult to find fossils of animals in this time, and likely because they hadn't arrived yet, but their prerequisites had. Plankton formed the base. Oxygen provided fuel. Nutrients cycled reliably. Genetic tools, the genes needed for multicellularity, differentiation, communication, were already present in ancient eukaryotes. All that was left was for Earth to get out of its own way. But it didn't, not yet. Instead, it plunged once more into ice, this time deeper, harder. Evidence from around 720 million years ago suggests the onset of what would become one of the most extreme climate events in Earth's history, the Sturian glaciation. Some models propose that the entire planet froze, oceans covered by kiln of ice, continents buried under snow, with only a few equatorial refugees keeping the flame of life alive. The term snowball Earth was coined for a reason. This wasn't just a chill. It was a lock. But why? What chain reaction pushed Earth this far? The answer is layered. It includes ongoing silicate weathering from exposed continental interiors, decreased CO2 from biological drawdown, changes in albedo due to increasing ice cover. The breakup of Rodinia, exposing more land near the equator where weathering is most effective. All these factors fed into each other, tipping the planet into an icy feedback loop. This was Earth testing the edge. But life astonishingly endured in cryosite holes, dark pockets on glacial ice where microbes generate warmth through photosynthesis. In subglacial lakes insulated by kilometers of frozen lid, in hydrothermal vents where superheated water provided warmth and minerals in the deepest darkness. Here in these scattered refuges, the biosphere contracted, huddled, and waited. And when the freeze finally lifted, when volcanoes poured enough CO2 into the sky to reverse the trend, to crack the ice and melt the seas, what emerged was not the same world that had frozen. It was richer, older, prepared. Because beneath the snow, the biosphere had not just endured, it had continued to change. The ice didn't break all at once. It wasn't a grand thaw, but a slow unraveling. A planetary exhale after a billion-year inhale. Volcanic gases crept into the sky, belching carbon dioxide from deep fissures and rift zones, building up a greenhouse veil thick enough to turn snow to slush, slush to flood, flood to ocean once more. As the glaciers withdrew, they scraped the land bare, leaving behind mineral-rich dust, powdered mountains, and the debris of a frozen world. All of it, calcium, phosphorus, silica, washed into the oceans, where it fertilized ecosystems poised for a renaissance. Nutrients surged. Algae bloomed. The biosphere compressed for so long into cryptic corners of ice and rock unfurled like a coiled spring. Life rushed back into the sea, not just in number, but in novelty. This was not the same biosphere that had endured the boring billion. The microbial communities of the past had been efficient, yes, but largely homogeneous, built from repetition and routine, honed to survive on slim margins and stable conditions. Now, with oxygen pushing ever higher, with nutrients spilling across the photic zone, the web of life grew thicker. More parts, more interactions, more opportunities. Oxygen levels already inching upward before the glaciation surged in its aftermath. This wasn't just oxygenation. This was transformation. The Earth's atmosphere began to resemble something closer to what we know. Not fully modern, but no longer an ancient haze. Ozone accumulated in the upper layers, shielding the surface from ultraviolet radiation. For the first time, complex life had a real chance to step onto land. And in the oceans, another quiet revolution was unfolding. Somewhere in the still warm shallows, cells were cooperating. Not just floating in colonies, but specializing. One set of cells becoming skin, another gut, another muscle, or something that might one day become those things. The leap to multicellularity, long teased in the fossil record through spiral impressions and branching filaments, now accelerated. Evolution began to play with form. Genetic evidence suggests the roots of animals. Metazoans may stretch back to this time, sponges perhaps, or sponge-like organisms filtering water, stabilizing sediments, leaving behind microscopic traces in layered rocks. Lipid biomarkers, cholesterol-related molecules associated with animal cells, begin to appear in rocks dating back to around 635 million years ago. These weren't just bigger life forms. They were coordinated. Tissues folded into functions. Energy was distributed. Oxygen used efficiently. Bodies, fragile and soft, yes, but real bodies began to sculpt the seafloor. And with them came consequences. Multicellular organisms disturb sediments, oxygenate deeper layers, stir nutrients. They reshape their environment simply by existing. This is called ecosystem engineering, and it's something life had barely done until now. But the moment bodies appeared, the world began to change in response to them. Predation likely emerged not long after. With size and complexity comes competition. Energy became something to hunt, not just something to gather. Some cells developed the machinery to move deliberately, to sense gradients, to respond to the presence of others. Evolution, once a matter of endurance, became a matter of interaction. Who could outmaneuver, outgrow, outlast? This was the beginning of what would become the arms race of life. Yet, even as the biosphere expanded and adapted, the chain reactions from Earth's earlier changes kept echoing. The planet still bore the scars of its glacial deep freeze. The oceans remained stratified in some places, with oxygen-rich surface waters hovering above deeper and oxic zones. These conditions would persist for millions of years, creating a patchwork world, safe havens and hostile depths, oxygen oases and chemical shadows. And the tectonic churn didn't stop. Gondwana, a new supercontinent composed of parts of what are now South America, Africa, India, Antarctica, and Australia, began to take shape. Its formation influenced climate, ocean currents, and nutrient flows, driving regional extinctions and radiations alike. The shifting of land continued to play Earth's slow baseline, steady beneath the melodic flourishes of life. Geochemistry records the rhythms in its own quiet way. Carbon isotope ratios shift, tracking changes in biological productivity and organic burial. Sulfur isotopes reflect redox conditions in the oceans. Strontium records the weathering of mountains. Together, these data points sketch the outline of a biosphere learning to respond dynamically to its own presence. In many ways, this is the real aftermath of the boring billion. Not just more life, but more connectedness, more chemistry between living and non-living systems, the birth of interdependence on a planetary scale. And still, Earth remained fragile. Each gain was precarious, each rise in oxygen hard-won and easily undone. Volcanism could tip the balance. Weathering could overdraw the carbon budget. A single large igneous province, one super-eruption, might dump enough CO2 or sulfur aerosols into the sky to freeze or fry ecosystems again. And yet over time, the balance held, not in a straight line, but in fits and starts, pulses of evolution, lulls of extinction. Complexity once introduced refused to retreat entirely. Life had found new strategies. Sex, multicellularity, predation, mobility, and these strategies became tools for resilience. By the end of this aftermath, the biosphere stood at the threshold of what we call the Ediacaring period, a time still shrouded in mystery, but full of unmistakable promise. Fossils from this time, quilted fawn-like impressions preserved in fine-grained sandstone, suggest the emergence of true macroscopic life, still soft-bodied, still enigmatic, but undeniably different. These were no longer just microbial mats or algal plumes. These were the ancestors of complexity, of animals, of ecosystems, of futures. And they only appeared because of what came before. The rifting of rodinia, the silicate weathering of tropical land masses, the slow drawdown of CO2, the glacial purges, the nutrient blooms, the oxygen spikes, the microbial innovation. Every quiet movement of the boring billion had set the stage. Every whisper of tectonic breath, every puff of microbial oxygen, every isotope shift, all of it stitched together into a prelude. And now the main act could begin. But Earth never forgets its prequels. Even now, deep in the ocean floor, we find ecosystems that echo those ancient times. Sulfur-cycling bacteria, iron-dependent archaea, microbial mats growing in pitch-black vents, breathing life into the chemical gradients once thought sterile and in our own cells, our mitochondria, our DNA repair enzymes, our lipid membranes. We carry the architecture built during that billion-year lull. We are not separate from it. We are its echo. So much of what we now call the explosion of life, the Cambrian, the rise of vertebrates, the march onto land, could never have occurred without the long preparation beneath quiet waters. A preparation that looked like nothing, but was everything. The boring billion didn't end with a bang. It ended with a transformation, not just of the planet, but of possibility. And that possibility, layered into rock, folded into cells, whispered through genomes, still resonates even now. To truly understand the boring billion, not as an isolated era, but as a chapter in the grand narrative of Earth, you have to widen the lens. Pull back higher, further. Let the continents shrink beneath your gaze. Let the eons flow like tides. Let the planets speak in rhythms instead of dates. Because Earth doesn't move in straight lines. It breathes in cycles, and each breath carries echoes of what came before. Before the boring billion, the world was loud. It had started in fire. The Hadean, a molten battering world, slowly cooled into the Archon when continents first began to form like scabs across a planet still fevered with volcanic heat. The oceans settled into basins. The first crusts hardened. Somewhere in that young stew, life flickered to life. Not all at once. Not with fanfare, but with molecules copying molecules. A whisper of self-replication beneath boiling skies. By 3.5 billion years ago, microbial life had already colonized Earth's oceans. Stromatolites, layered mounds built by cyanobacteria, rose from tidal flats. These mats were slow builders, catching sediment, binding it with sticky biofilm, and growing skyward toward the sun. They're still found today in a few rare corners of the world, living fossils from a time when oxygen was a poison and the sky was hazy with methane. Then came the first great disruption, the Great Oxidation Event, around 2.4 billion years ago. Before that, Earth's atmosphere was rich in methane and carbon dioxide, warmed by greenhouse gases and colored by photochemical hazes. But cyanobacteria, those blue-green architects of the shallows, had begun to exhale oxygen. Slowly, invisibly, they flooded their world with it. At first, that oxygen was swallowed up by iron in the oceans, precipitating out into red bands that still stripe cliffs today. But eventually, the system filled. Iron could no longer mop it up. Oxygen spilled into the air, and the air changed. It wasn't a celebration. It was a catastrophe. Anaerobic life. Organisms that thrived in oxygen-free conditions were poisoned. Mass extinctions followed. Methane broken down by oxygen collapsed, triggering a massive cooling event. Some scientists believe the first global glaciation, the Huronian, was a direct result of this oxidative tipping point. A sudden snowball Earth, life choked on its own breath. Still, from that chaos, something new began. Cells began to use oxygen not just as a threat to survive, but as a tool, a potent electron acceptor, a fuel for respiration. Life rewrote its chemistry. Eukaryotic cells emerged, possibly through endosymbiosis, one cell engulfing another and keeping it, turning it into a mitochondrion. And from that strange partnership came the foundation for all complex life. This was the run-up to the boring billion. So when we say that the boring billion was uneventful, what we're really saying is that it was a long exhale after the drama of transformation, a time when Earth's systems, after a violent leap forward, settled into something more stable. Photosynthesis continued. Oxygen flickered in shallow seas. Eukaryotes diversified slowly. It was the developmental stage, not infancy, not adulthood, but a kind of planetary adolescence full of awkward growth and unseen change. And then when the boring billion ended somewhere around 720 million years ago, the volume turned up again. Earth plunged into Neoproterozoic snowball Earths, beginning with the Sturian and followed by the Merino and glaciations. These weren't mere winter flurries. These were continental scale freezes. Glacius reaching to the tropics, oceans locked in thick ice, atmospheric carbon dioxide plummeting to precarious lows. If you'd been there to look from orbit, Earth might have looked like a marble of white, and yet life held on. How? Perhaps in refugia, volcanic lakes, geothermal seeps, cracks in the ice where sunlight could filter through brine. Perhaps in the simplicity of microbes, already masters of surviving extremes. Either way, the biosphere contracted but endured. And when the thaw finally came, when volcanic outgassing released enough greenhouse gas to break the grip of snow, life flooded back with force. From this emerged the Edie period, marked by strange soft-bodied organisms whose fossils still puzzle paleontologists. They left impressions in ancient sands, quilted, radial, fawn-like creatures. Some lay flat. Some may have stood upright in currents. Some seemed to move. Others did not. We still don't know exactly what they were. Early animals, a now extinct lineage, a biological experiment that led to nothing. Whatever their identity, they signal that life was no longer content to be small and single-celled. And then came the Cambrian explosion, the moment most schoolbooks start to pay attention. Around 541 million years ago, animal life diversified with unprecedented speed. In the blink of geological time, creatures with eyes, legs, shells, and segmented bodies burst into the fossil record. Predators and prey, burrowers and swimmers. The ancestors of aeropods, mollusks, chordates. Evolution's pace, once glacial, became a wildfire. But again, it only burned so brightly because of what had come before. The oxygen from earlier eons had finally reached sustainable levels. The genes for development, things like hawk genes, which control body plans, had already evolved during the quiet centuries. Multicellularity had been tested and refined. The raw ingredients of complexity had been stewing for hundreds of millions of years. The Cambrian wasn't a spontaneous eruption. It was a long pressured release. The lesson whispered through each layer of rock is this: Earth changes in cycles. Boom and lull, spark and silence, fire and freeze. The boring billion is not an exception to this pattern. It's one half of it, the inhale before the exhale, the rest before the sprint. It was long, yes, and it was slow, but it was also necessary. Even today, we see the rhythms continue. The rise and fall of biodiversity through the 5 major mass extinctions. The Endervision, the Late Devonian, the End Permian, the End Triassic, and the End Cretaceous. All came in pulses, sometimes linked to volcanism, sometimes to climate, sometimes to impacts. Each extinction was followed, not immediately but gradually, by renewal. Evolution resets. Patterns recur, and behind those patterns are the same engines that drove the Proteroic. Plate tectonics, solar flux, volcanic cycles, carbon drawdowns, biological feedback loops. The orchestra plays the same notes, only the instruments change. Some scientists now speak of the Anthropocene, an epoch marked by human influence, not just culturally, but geologically. We move more sediment than all the world's rivers. We alter the carbon cycle. We change the atmosphere, shift nitrogen flows, warm oceans. We, like cyanobacteria once did, are becoming a planetary force. And just like them, we risk tipping systems we don't fully understand. That's not to say we're doomed, but it is to say that the boring billion offers a lesson. Not all change is immediate, and not all slowness is safety. 1 billion years of microbial breath nearly collapsed the biosphere. A few degrees of global temperature shifted too quickly can echo for millennia. Earth moves slowly, but when it moves, it carries everything with it. It also teaches us about resilience, because life, small, adaptable, stubborn life, has always found a way through ice ages, through oxygen shocks, through continental shuffles and sulfur surges. Life doesn't require stability. It requires flexibility. It builds its future not in explosions, but in networks, in small interdependencies, coevolutions, mutualisms. We inherit that legacy. Our lungs breathe oxygen molecules released by ancient bacteria. Our cells run on mitochondria, forged in protozoic symbiosis. The bones in our ears, the patterns in our genes, the cycles in our climate, all trace back in spirals and folds to the world shaped in the boring billion. To view that billion years as empty is to misunderstand what creation looks like on a planetary time scale. It isn't glamorous. It isn't noisy. It is patient. It is iterative. It is fundamental. So the next time you look at a mountain, or watch the tide roll in, or breathe under a canopy of green, remember those things did not come from the age of drama. They came from the age of endurance, from a world that took its time, from an era where every quiet moment was a preparation, and from a billion years that were only boring if you weren't paying attention. Science doesn't always begin in labs. Sometimes it begins in boots, caked with red dust, standing on ancient ground, listening not for voices, but for patterns. The story of the boring billion isn't just the story of Earth's stillness. It's the story of the people who noticed that stillness and asked why, and sometimes was it really still at all. For decades, geologists referred to the interval from roughly 1.8 to 0.8 billion years ago as uneventful. The fossil record seemed thin. The geochemical signals seemed muted. Oxygen levels were low. Biological complexity didn't appear to move much. And tectonic activity looked quiet on the surface. It was the calm center of a long tail, a necessary bridge, but not a starring role. That view began to shift, not with a single paper, but with a slow accumulation of questions, a compass twitching the wrong way, an isotope ratio that didn't fit the model, a strumentolite in a place it shouldn't be. Little inconsistencies that over time began to whisper something different. And it was the scientists who kept listening that brought those whispers to life. Take Roger Buick, for instance. Working across ancient terrains in Australia, Buick was among the first to propose that the early Earth, long before the boring billion even began, was already shaping its surface chemistry through biology. He studied ancient strumentalites and carbon isotopes, arguing that microbial life was influencing global carbon cycles over 3 billion years ago. But his work also carried forward into the quieter stretches of time. He hunted biosignatures where others saw blankness, and in doing so, helped establish that boring did not mean empty. Then there's Timothy Lyons, a geochemist who became one of the leading figures in rewriting the story of Earth's oxygenation. Lyons' team pioneered the use of metal isotopes, especially molybdenum, chromium, and uranium, to track subtle changes in ocean chemistry. These elements behave differently, depending on oxygen levels, and when buried in black shells, they carry those chemical stories forward through time. By analyzing shales from different parts of the boring billion, Lyons showed that the ocean's chemistry was not flatlined, but oscillating. Oxygen came and went. Euchia waxed and waned. There were peaks, valleys, and patterns, not noise, but rhythm. What had looked like stasis became a landscape of pulses. In South China, geologist Shuai Zhao was digging through rocks from the mid-Proterozoic and finding something curious. Fossils, not big ones, but structured ones, cells with thick walls, clusters that suggested cooperation, some possibly eukaryotic. His work alongside others in the Dachshund 20 formation uncovered exquisite microfossils from just after the boring billion fossils that hinted their ancestors had been around long before. Others like Susanna Porter looked at acryarchs, enigmatic microossels whose shape and complexity increased over time. Though they don't leave bones or shells, they do leave beauty. Spirals, spines, petal-like ridges. Porter's work helped trace their evolution across the mid-Proterozoic, showing that eukaryotes were not idle. They were experimenting morphologically, genetically, even if they hadn't yet leapt into the fossil record with limbs and skeletons. And then there's Noah Planovsky, whose work bridged the gap between biology and geochemistry. Planovsky was one of the first to demonstrate through chromium isotopes in ancient soils that small but persistent oxygen oases existed even during Earth as supposedly anoxic stretches. These localized zones of higher oxygen might have been near shorelines or nutrient-rich upwellings, places where microbial mats and early algae pushed O2 into the air and water just enough to shift local redox conditions. His work helped unravel the myth that Earth's surface was either fully oxic or fully anoxic. It was patchy, variable, messy, and within that patchiness, complexity could evolve. Across continents, researchers began revisiting old samples, pulled decades earlier, archived in drawers and warehouses, dismissed as geologically unremarkable. They sliced these rocks thinner, measured them more precisely, applied techniques that hadn't existed when the samples were first drilled, and again, they found new signals, sulfur isotope anomalies, iron speciation ratios, biomarkers tucked into bitumen. In Canada, in the Gunflint Iron Formation, some of the oldest known microossels were discovered, preserved cellular structures that hinted at both cyanobacteria and potentially more complex organisms. These fossils are not flashy. You wouldn't recognize them without a microscope. But in the hands of scientists trained to see structure in specks, they became maps leading backward through time. In Namibia, researchers working in the Atari group uncovered signs of redox stratification in ancient oceans, supporting the idea that deep water remained anoxic even as surface waters fluctuated. These subtle gradients invisible to the eye might have shaped evolution more than any extinction. And in Siberia, data from the Sakaya-Tunguska Basin offered additional evidence of oxygenation events that predated the Cambrian by hundreds of millions of years. Not just one great oxidation event, but a series of pulses, small rises, plateaus, and crashes that formed a breath-like pattern across the billion years. What ties all these discoveries together isn't just the technology. It's the persistence, the willingness to look again, to ask whether silence might contain signal, and perhaps most of all, the collaboration. Paleontologists, geochemists, stratigraphers, evolutionary biologists weaving their data together like threads in a tapestry too large for any single pair of hands. This shift wasn't only about Earth's chemistry. It was about Earth's story. By re-examining the boring billion, these scientists weren't just updating graphs. They were challenging a deeply human bias, the belief that only drama makes history, that only explosions matter. But evolution doesn't always sprint. Sometimes it lingers. Sometimes it waits for a window, a break in the storm, a flicker of oxygen, a sliver of habitat, and then quietly it moves. And in the quiet, people noticed. To study a billion years of stillness is to make peace with patience. The scientists who pursue this work do so not in search of spectacle, but of meaning in the nearly imperceptible. They stand in deserts, beside cliffs on mountain ridges where ancient seabeds now rise into sky, and they chip away at stone, not for what it reveals at once, but for what it might whisper after years of scrutiny. And so much of that whispering happens after the fieldwork ends. A slab of shale scraped from an outcrop in Namibia might spend decades in a drawer before someone like Linda Carr picks it up and runs it through a mass spectrometer. A core drilled from the Canadian Shield may hold within it not just rock, but stories of redox transitions of sulfur moving through ancient seawater, binding with iron, forming pyite under a dim sun. The truth of the boring billion was not hidden. It was simply quiet. Field notebooks from these expeditions often read like strange poetry, not in their language, but in their restraint. Meter 47.8. Shale becomes darker. Faint sulfur odor. Possible microbial matte texture. That's it. But behind that note might be a shift in isotopic signatures that rewrites an entire timeline. A few cm of stone could capture a pulse of oxygen, a bloom of algae, a whisper of eukaryotes daring to try something new. There's a kind of romantic stoicism in this kind of science. No explosions, no dinosaur skeletons, no cataclysmic impact layer, just thin sections under microscopes, data tables stacked like sediment, and questions that hang in the air for years before settling into anything like an answer. For Gerard Way, a blind paleontologist and evolutionary theorist, The boring billion isn't boring at all. He speaks of evolution as escalation, of arms races, not just among predators, but among ideas. And he reminds us that seeing isn't the only way to detect pattern. Sometimes you feel it. Sometimes you trace it across the record, like a braille trail through the rock. And then there are those who wrestle with time itself. How do you think in billions of years? James Casting, a planetary scientist and climate modeler, has spent decades trying to answer that, not by staring at rocks, but by modeling ancient atmospheres. His simulations of greenhouse gas feedback, solar evolution, and Earth's climate stability show how fragile the line is between icehouse and greenhouse, between microbial stasis and planetary revolution. His work reveals how biology nudges climate, how climate pushes back, how over geologic time, it's not balance that wins, but adaptability. And what of Rachel Wood, a geobiologist who has traced early reefs through time? Her work explores the slow, quiet rise of skeletal life. Not the flashy Cambrian forms, but the forerunners, those whispering reef builders that may have pioneered the carbonate scaffolds long before corals took their throne. She reminds us that structure is also a fossil, that even the ways organisms built their homes carry evolutionary meaning. One of the most enduring questions of this field isn't just what happened, but how do we know? That's where radiometric dating enters, a discipline that itself feels like magic. Scientists like Sam Bing, who passed in 2019, revolutionized our understanding of geological time through high-precision uranium dating. His work brought accuracy to the previously vague boundaries of Earth's timeline, pinning the ED, the Cambrian, and even key pulses of oxygenation to within a few hundred years, in a world measured in billions that's nearly surgical. His legacy is not just in age brackets, but in anchoring the abstract, turning somewhere around 1 billion years ago into 987 million plus or minus. 3, giving precision to the poetic, and by doing so helping the rest of us understand that this long breath of planetary calm at edges chapters transitions. And then there are the thinkers, the philosophers of deep time. What does it mean to know that 1 billion years passed without a tree, a bird, a voice? What does it do to the human imagination to hold that much time in your head? Writers like Mesha Bornerud have spoken to this, to what she calls timefulness, the practice of learning to think with geologic time, not as background, but as context. She argues that Earth's story should not be reduced to a series of explosions and events, but appreciated for its durations, the long stretches where the most meaningful changes were not visible but structural. In the classroom, students are often taught to rush toward the Cambrian to find comfort in trilobites and teeth. But the geocontists who live in the boring billion teach a different lesson, that life's true miracle was not invention, but persistence, not drama, but discipline. Because for every dramatic extinction, there is a long, unremarkable persistence that makes recovery possible. For every innovation, there are 1 million failed attempts. For every great leap forward, there is the inching, stumbling rehearsal. And it is in the boring billion where Earth learned to rehearse, to oxygenate without catastrophe, to evolve without resetting, to inch with excruciating patience toward a world that could sustain bodies, complexity, breath. The scientists who study this time are not just historians. They're time translators, rock readers, patient specialists. Their work reminds us that awe isn't always explosive. Sometimes it's sedimentary, layered, quiet, but permanent. What does it mean to measure the past? Not just the stories that happened, but the chemistry of what changed. The breath of the oceans, the colors of the sky, the weight of 1 billion-year-old moment. The boring billion didn't leave us with fossils of dinosaurs, or forests, or claws. It left us something quieter. Layers of mineral memory, chemical hints, isotopic footprints. And to read them, scientists don't just dig, they measure, they model. They interpret with instruments that can see into atoms, they can hear the trace echoes left by vanished atmospheres. This is where geology meets forensics, and Earth's still age becomes its most sensitive record. Start with the isotopes. Isotopes are versions of an element with different numbers of neutrons, like different dialects of the same language. Carbon-12 and carbon-13, sulfur-32 and sulfur-34, uranium-238, decaying ever so slowly to lead. They behave slightly differently during chemical reactions. They fractionate, prefer one compound over another, and those preferences get locked into rock. Take carbon isotopes. When life is busy, when photosynthesis is booming, it preferentially uses carbon-12, the lighter isotope. This leaves behind an ocean slightly enriched in carbon-13, which is recorded in carbonates. A spike in 13C often signals a burst of biological productivity, a crash, maybe an extinction, maybe a change in ocean circulation, maybe a world holding its breath. These patterns are plotted across time, are called D13C excursions, and the boring billion is full of them. Not flat, not silent, but pulsing. Then there's sulfur, the ancient element that cycles between atmosphere, ocean, and rock. Sulfur isotopes tell us about redox states, how much oxygen was present. Microbes that process sulfur, like sulfate-reducing bacteria, leave behind isotope patterns that only occur under certain conditions. If you see a wide range of sulfur isotope values in a sediment, it might mean localized oxygen oasis. If you see mass-independent fractionation, a weird pattern from ultraviolet splitting in the upper atmosphere, it could mean an anoxic sky. These signals help date the oxygenation events, the quiet rises and falls of breathable air. But even more delicate are the trace metal isotopes. Chromium, molybdenum, vanadium, iron, uranium. Each one whispers something different. Molybdenum is sensitive to the redox state of the ocean. Under oxygenated conditions, it's soluble and mobile. But when the ocean becomes filled with hydrogen sulfide, it precipitates out and gets locked into black shells. A high moation in shale often means an ocean margin with active urea and surface oxygen. Chromium behaves differently depending on whether oxygen is present in soils. Chromium isotopic values in paleos. Ancient soils have been used to detect terrestrial oxidation as early as 800 million years ago. It's one of the reasons we now believe oxygen oasis existed long before full atmospheric oxygenation. Iron speciation is another key. Iron comes in several oxidation states, and by examining the ratios of different iron minerals, ferric oxides, ferrous carbonates, pyite, geologists can reconstruct whether an ancient water column was oxic, anoxic, ferruginous, or eukenic. These distinctions matter. The Mid-Mesozoic oceans weren't all one thing. Some were rich in iron, some in sulfur, some in oxygen. Each zone shaped life differently. Then there's uranium, which helps us date all of this. Uranium decays to lead over billions of years at a rate so steady it has become our cosmic clock. By measuring the ratio of uranium to lead in Zer crystals, tiny durable grains found in igneous rocks, geologists can assign precise ages to rock layers. These dates anchor everything. Without them, the oxygen spikes and climate swings would just be floating data. Uranium ties them down, turns narrative into chronology. And this dating feeds into radiometric timelines, detailed stratigraphic columns where every layer, every isotopic excursion, every microocell sits on a scaffold of time. We can look at a shale in China, match it to a limestone in Namibia, compare it to a volcanic ash bedded in Canada, and say these happen together. And from that, a global story emerges. But chemical traces only tell us part of the story. The other half is told by climate models, virtual Earths built on physics and run through supercomputers. These models simulate how sunlight, greenhouse gases, ice, and OS. They help explain why a billion years of low CO2 didn't freeze the planet completely, why glaciations came in pulses, how continents at the equator increased weathering and CO2 drawdown. Models also test biological feedbacks. What happens if plankton productivity spikes? Oxygen rises, organic carbon burial increases, CO2 drops, cooling begins, weathering slows, oxygen drops again. These are not guesses. They're feedback systems running under the hood of our real planet, and models help make sense of their timing. Even the sun is modeled. It was fainter in the Proterozoic, maybe 85 and 90% of today's output. So why wasn't Earth a snowball all the time? The faint young sun paradox remains partly unsolved. But models suggest that greenhouse gases, volcanic outgassing, and cloud feedbacks might have compensated. Again, it's not a single answer. It's a system balanced barely for 1 billion years. And whether models and isotopes converge, another tool arises: genomics. Molecular clock studies using DNA mutation rates to estimate when lineages diverged suggest that many genes critical for multicellularity evolved during the Boring Billion. Genes for cell adhesion, for communication, for signaling. We don't have animal fossils yet, but we have the genetic scaffolding. It was built in the quiet. And just as geology feeds into biology, biology now feeds into astrobiology. Because if life could survive, even evolve during 1 billion years of low oxygen, shifting climates, and stratified oceans, then perhaps life on other planets might do the same. Proterozoic Earth becomes our template for habitability. Not the lush rainforests of the Carboniferous, not the coral seas of the Mesozoic, but the muted, microbial, metabolically inventive world of the Boring Billion. This is why scientists study it so obsessively. Why cores are drilled from buried cratons. Why ancient stromatolites are mapped with laser scanners. Why sulfur ratios are measured to the 5th decimal place. 'Cause in those measurements, we're not just seeing Earth, we're seeing possibility. Possibility for life elsewhere, for the resilience of biospheres, for the quiet stages of evolution that build everything loud. And it's not only about space. Studying these slow, stable feedbacks also helps us understand what modern climate instability really means. 'Cause we now know what a balanced Earth looks like. We've measured it, modeled it, seen how fragile that balance is, how easily a few degrees of warming or a shift in carbon burial can flip the whole system. In a world where CO2 rises by the year and feedbacks are accelerating, the Boring Billion stands as both contrast and caution. A time when Earth maintained balance, not because it was strong, but because it was quiet. And now it's not. To know the Proterozoic, truly know it, is to listen to things long vanished. Things you cannot touch or see or even fully imagine. Because even after isotope ratios and models and timelines, much of what we reconstruct rests on inference, on absence, on the ghost traces left behind by ancient oceans, glacial floods, and vanished genes. And so we turn to sediment. Glacial sediments in particular are some of Earth's most eloquent archives. They're messy. Yes, gravel dumped by melting ice, clays smeared by retreating glaciers, drop stones scattered through deep sea muds. But inside that chaos lies precision. A single cobble embedded in a fine-grained shale far from shore tells you that an iceberg passed here, and that there was ice at sea, and that somewhere upstream a glacier carved into water. Multiply that by thousands of locations, and you begin to map the cryogenic Earth. We use Tillites' lithified glacial tills to understand where ancient ice once scraped bedrock. Their minology can tell us what kind of rock was being eroded, how far it traveled, and what the conditions were during deposition. The presence of street-parallel scratches on underlying rock shows the direction of glacial movement. These are old signals buried for 1 billion years, and yet we can still follow their paths. Then there's cap carbonates, those weird thin layers of carbonate rock that sit directly on top of glacial deposits. They shouldn't be there. Why would tropical-style carbonate sediment, the kind usually formed in warm, shallow seas, sit right above a layer of ice-scoured tillite? Because after a snowball Earth event, the planet rebounded fast. CO2 had built up in the atmosphere to massive levels. And when the ice finally melted, a greenhouse overshoot followed. Global temperatures soared. Oceans turned acidic. The cap carbonate was laid down rapidly, often in just tens of thousands of years. A blink geologically, and its isotopic values reflect this chaos. Light carbon stripped from volcanic CO2 and decaying biomass floods the sediment record. A fingerprint of abrupt climate swing. And in the cap carbonates, we find tiny tubes. Claudina namicolathis. Maybe not from the boring billion, but close after. They're the first creatures to build external skeletons. Their origin may have been seeded by the long, quiet metabolic and genetic experiments during the billion years prior. A world without predators had finally built the tools to defend against them. But the rocks aren't just about ice and shells. Sometimes they're chemical fossils. Certain molecules like A's and strains are biomarkers, chemical remnants of once living organisms preserved over eons. Hopins are associated with bacterial membranes, strains with eukaryotic ones. Their relative abundance in ancient sediments helps reconstruct the biosphere. If you find a rise in strains, you might be looking at the quiet rise of complex cells. The slow, almost invisible revolution that would eventually produce animals. These are not dramatic fossils. They're oil molecules, sometimes smeared across rock, sometimes trapped in tar, but they are life shadows, and we read them like runes. Even more subtle is the work happening at the edge of molecular paleontology. Attempts to extract ancient DNA, or at least its echoes. No actual DNA survives from the boring billion. The molecules are far too fragile. But by comparing the genomes of modern organisms and modeling their rate of change, scientists can reconstruct ancestral genomes. This is how we estimate when the first mitochondria entered eukaryotes, or when certain metabolic pathways evolved. These genetic time machines, called molecular clocks, let us peer back into a world with no bones, no shells, and yet an explosion of inner complexity. The genes for multicellularity, for adhesion, for cell signaling, they didn't emerge in the Cambrian. They emerged quietly in scattered eukaryotes during the boring billion. And by studying sponges, chungiflagellates, and algae today, we can map the evolutionary paths that likely began then. Meanwhile, in the world of astrobiology, scientists modeled Proterozoic Earth as a testbed for exoplanets. It turns out that planets with microbial biospheres, high methane, low oxygen, long durations of stability, are probably more common than those with forests and tigers. If life exists elsewhere, it may look more like Proterozoic Earth than Jurassic Earth. So researchers build atmospheric models using mid-Proterozoic gas compositions, run simulations on exoplanet climates, and look for biosignatures that might match. The dull, stable, microbially dominated Earth of the boring billion has become a template for other worlds. What used to be written off as Earth's least interesting chapter is now seen as a critical evolutionary bottleneck. The place where life built the scaffolding for everything else. Not the leap, the launch pad. And for Earth system scientists, the biggest revelation is how tightly everything is interconnected. The carbon cycle isn't just about rocks. It's about photosynthesis, burial,